We now begin with reactions of alkene. See, if you remember, when I talked about alkane, so we are now talking about reactions of alkene. See, alkane was less reactive because of only one reason, and that is that the carbon-carbon bond was sp3-sp3 overlap, hybrid orbital overlapping with a hybrid orbital. The bond strength is more. So for a basic funda chemical reaction, bond has to be broken so that reactants will then get converted into product. Whereas in the case of alkene, the number of chemical properties we're going to have is very large. Only because of one reason is that we have a pi bond, which is a weak bond, and across there. So mostly the first question that we have to answer is, what kind of a reaction, the characteristic reaction shown by. So this is what I am trying to teach you from the JEE NEET angle. Okay, the characteristic reaction the characteristic reaction shown by alkene, is an electrophilic addition. So remember this is one question on its own. So what do we mean by addition? Addition means two or more reactants have formed a single product. So the first reaction that we are coming across over here is addition of hydrogen. Addition of hydrogen or hydrogenation. Remember, from the exam point of view, the entrance exam point of view, heat of neutralization, combustion, hydration and hydrogenation. These are four definite reactions which are always exothermic. You should not confuse. We may use some heat to initiate the reaction, but at the end, in the total, it is exothermic reaction. Is this clear? So, we can call this as formation of alkane or formation of alkane or the Sabatier-Sanderson reaction. So all this means the same. Basically what happens? You have an alkene, CH2 double bond CH2, bubble hydrogen gas in presence of finely divided Raney nickel. At a temperature, if I heat it, it's around 450 Kelvin approximately we require. And what happens is you get an alkane CH3. Is this point clear? So this is the first reaction. Now the second reaction that we have to talk about is, I told you that is addition of halogen. So the second reaction that we have is addition of halogen. So obviously it's electrophilic addition. Okay. The next question that we have to talk about for what you call JEE NEET will be, what do we talk about? The reactivity, decreasing order of reactivity. Decreasing order of reactivity will be chlorine greater than bromine greater than iodine. We have fluorine, but then fluorine reacts with what you call all hydrocarbons and forms carbon tetrafluoride. So actually fluorine will be the most reactive, but we will not achieve our purpose of the addition reaction. Is this point clear? So this leads to a formation of vicinal dihalide. So what happens is, if you have CH2 double bond CH2 plus bromine, this reaction happens in presence of carbon tetrachloride or acetic acid as what you call solvent. So this would be a non-polar solvent here, and what will happen, you will get CH2 Br CH2 Br. It's a vicinal dihalide. You get a vicinal dihalide. That means the halogens are on adjacent carbon atom. So this will be ethylene dibromide. This is ethylene dibromide. Okay. Now ethylene dibromide has a very important use. It is used for fumigation of food grains. So when you are exporting food grains, in the container you pump ethylene dibromide so that worms cannot survive in that condition. So this will be a connection of the reaction to the uses. Okay. So when I talk about the mechanism, so you have CH2 double bond CH2. So when you have bromine Br2 in presence of carbon tetrachloride forms Br plus Br minus. Br plus is called as bromonium ion. It's called as bromonium ion. So when it attacks, Br plus attacks, what happens is that it forms, so there's a shift in the bonded pair of electron, okay, electromeric effect, complete transfer of bonded pair of electrons. So this becomes negative. So you have the intermediate carb anion. So you have CH, Br, and your carbonium ion is over here. So here now the bromide attacks. This is called as trans attack. So it will not attack from the same side as bromine. The reason is because bromine is a very large atom. It's going to cause physical obstruction, which in chemistry we call as steric hindrance. So always this will be a trans attack, and you will end up getting CH2 Br CH2 Br, ethylene dibromide. So this was about halogen. We now come to the next reaction, the third reaction, that is addition of halo acid. Obviously the first topic that we are going to discuss is the reactivity. So that is obviously for our JEE NEET. What happens is reactivity is what? Reactivity is HI greater than HBr greater than HCl. Obviously you will ask why? HI, the bond length is more. So if the bond length is more, it is weak, and so it can be broken very easily. Is this point clear? So if you have CH2 double bond CH2 plus what will you have? Let us say HBr. So what is going to happen? This will form CH3 CH2Br. So this gives rise to, so addition of halo acid gives rise to an alkyl halide. So this becomes ethyl bromide. Ethyl bromide. Is this point clear? So now, what would be the mechanism? The mechanism is what happens. HBr splits to form H plus Br minus. So over here your H plus is the electrophile, which is going to cause the attack. So what will happen? We have we have CH2 double bond CH2 plus H plus, Okay, so what is it going to form? This is going to cause a shift in bonded pair. So you have CH2 plus and you have CH3. So the intermediate of electrophilic addition of halo acid is a carbonium ion. Carbonium ion means what? A carbon which has got a negative or positive charge. Carbocation or carbonium ion. And now this is good. Of course, the trans effect, what will happen is, in this case you will have CH, then the Br minus will attack. This is a fast step. So you have CH2Br, or we can write it as CH3 CH2Br. Okay, ethyl bromide. Now I have been considering over here symmetrical alkene. What happens in case of an unsymmetrical alkene? In case of an unsymmetrical alkene, we have what we call as the Markovnikov's rule to follow. So, what is Markovnikov's rule? So, according to Markovnikov's rule, what we have is, when an unsymmetrical reagent adds to an unsymmetrical alkene. So we have, when an unsymmetrical reagent adds to an unsymmetrical alkene. When an unsymmetrical reagent adds to an unsymmetrical alkene, the negative part of the reagent, goes to that carbon having least number of hydrogen. So why we will explain, okay, in the mechanism. So we have to take CH3, CH double bond CH2. So this is propene. So you can see over here across the double bond, this is CH2 and this is CH3CH. So it's an unsymmetrical alkene. Now this reacts with HBr, suppose. So your reagent is also unsymmetrical. Why? Because if you keep across the bond, you have H over here and Br over there. So HBr is a unsymmetrical reagent. So when they add, what happens? The negative part will go to that carbon having least number of hydrogen. So we have CH3, CHBr, CH3. So you get 2 bromopropane. You get 2 bromopropane. Is this clear? Why is it so? So for this, we have to understand the mechanism of what you call so let me see if there is space. Yes. So we are now talking about mechanism of Markovnikov addition. See, what happens in the mechanism is, as I told you, it's an electrophilic addition. So when I take propene, CH3, CH double bond CH2, and I react with HBr, so H plus is the attacking reagent. So there's a shift in the bonded pair. So there are 2 possibilities. What are the 2 possibilities? You get CH3, CH plus CH3, or the other possibility, this is structure number 1, or the other possibility CH3, CH2, CH2 plus. So here you can see in the first structure, okay, in the first structure this carbonium ion is secondary, and here you are in the second structure, here in the second structure the carbonium ion is primary. I had taught you in the concept of hyperconjugation that stability of carbonium ion is tertiary greater than secondary greater than primary. So obviously this is a more stable carbocation. So this is formed, is this point clear? So what happens is, now this is attacked by the Br minus, and what do you get? You get CH3, CHBr, CH3. So this is the mechanism of what you call Markovnikov's reaction. Now what happens is, along with Markovnikov's reaction, we have something else called as, what I would say, peroxide effect or a Karash-Mayo effect. Is this clear? So that would be called as an anti-Markovnikov addition. So we continue the addition of halo acid. We are now coming to what we call as peroxide effect. Or it is also called as Karash-Mayo effect, or it's also called as anti-Markovnikov addition. See, what happens in this case is, if we take now, what are the main conditions? First is, how does the reaction take place? It takes place by free radical mechanism. It takes place by free radical mechanism. Yeah, that's the first point. It takes place by free radical mechanism. Then the second point is what? That this reaction is only true for HBr. So it does not work for HCl, HI. It's only true for. So what is happening over here is, you have propene CH3 CH double bond CH2 plus HBr in presence of, let us say, benzoyl peroxide or hydrogen peroxide. And what happens is, you get CH3 CH2 CH2Br. So this is one bromopropane. I mean, in Markovnikov's addition it was 2 bromopropane, this is 1 bromopropane. So why is it so? We can explain this by looking at the mechanism. So when we are talking about the mechanism, what happens is, listen carefully. We have, let's start like this, step 1. So if you have a peroxide ROOR, R can be H or R can be a aryl group, benzoyl peroxide. I told you we prefer benzoyl peroxide. So what is going to happen? Benzoyl peroxides are unstable. So it is going to decompose, the oxygen-oxygen bond is going to decompose, and you get a free radical. So RO, when I put this red dot, it is an unpaired electron. So this is a free radical. So now step 2, what happens is, this RO, the free radical, This RO, a free radical, reacts with HBr. It forms ROH, leaving behind bromine free radical. Leaving behind bromine free radical. Now this bromine free radical, so this will be bromine free radical. So what happens is the next step, step 3, the bromine free radical, I'll add the dot, I'll do it now only. So the bromine free radical attacks the alkene. So you have CH3, CH double bond CH2. So when it attacks, there are two possibilities that can happen. You have CH3, CH, CH2Br. So you have a free radical here. Or the other possibility is you have CH3, CH2, CH3, CHBr and then CH2. So you will have your free radical, the electron over here. Now stability of carbon free radical is given by what? So these are themselves a question in entrance exam. Stability of carbon free radical is tertiary greater than secondary greater than primary. So you can understand over here, this will be more stable. So if this is more stable, this is what is going to get formed. So what will this do? This secondary free radical, step 4, So this is, now we are coming to step 4. So we have CH3, CH, CH2Br. Okay. This free radical reacts with HBr. And what does it form? It forms CH3, CH2, CH2Br plus what does it leave behind? It leaves behind a bromine free radical. It leaves behind a bromine free radical. So this bromine free radical is now going to attack one more propene, form this, that's going to attack another HBr. So chain initiation, chain propagation, and this will be somewhere when it gets over, it will be chain termination. Is it clear? So we said this is chain initiation, chain propagation, and somewhere it will get terminated. Is it clear? So 3 steps for any mechanism involving free radical mechanism. Now you will ask me why HCl and HI do not follow this reaction, because in this case all these 4 steps which I have enumerated, they are all what you call exothermic. They are exothermic. So when they are exothermic, what happens is that reaction goes in the forward direction. With HI and HCl, these 2 reactions are endothermic, and so it does not happen. You will tell me, sir, if it is endothermic, why not we supply heat? If we supply heat, peroxide will decompose very fast. Is this point clear? So it is, whether the egg is first or the chicken is first wala case. So we take it for granted that it's not reacting. So this is about Karsh-Mayo effect, peroxide effect, or anti-Markovnikov addition. Is this clear? So we are now talking about addition of concentrated sulfuric acid. So we begin this by understanding the structure of sulfuric acid. See, sulfuric acid has a structure of S double bond O, OH, OH. So what happens is, this H plus comes out, and so you get H plus OSO3H minus. I never prefer to use HSO4 minus, because then you don't know the charge is on which oxygen. So OH split out over here. The proton did oxygen, the proton came out leaving behind oxygen minus OSO3H. So it becomes easy to understand. It was that oxygen which had negative charge. This is clear. So when I react, let us say we have CH2, double bond CH2 plus the first molecule of sulfuric acid concentrated, H2SO4. So you have, this has split to form H plus OSO3H minus. So obviously it's an electrophilic addition. So H plus attacks, and what do you get? You get CH3 CH OSO3H. Okay. Now this is ethyl hydrogen sulfate. This is ethyl hydrogen sulfate. So this is formed. But then why are we teaching you this reaction is because that this ethyl hydrogen sulfate CH3CH HOSO3H. It is clear. Now this on hydrolysis. So what is hydrolysis? Hydrolysis we say is splitting, breaking or decomposing a bond by using water. Hydrolysis, splitting by using water. What happens? You get CH3 CH2OH plus again H2SO4. So this is one of the methods of preparation of alcohol. So this is ethyl alcohol. Now what happens in case of branched higher alkene? Okay, you don't get the intermediate only. So if you have isobutylene, CH3 double bond CH2 CH3. In case of isobutylene, the reactivity is more. So directly the water gets added, not through an intermediate in presence of sulfuric acid. What do you get? You get CH3, CH3, CH3OH. This is tertiary butyl alcohol. This is tertiary butyl alcohol. Are you understanding? So this is about what you call addition of concentrated sulfuric acid. We come to the fifth reaction, that is addition of hypohalous acid. Addition of hypohalous acid. See, what happens is when you react, say, chlorine with water, it forms HCl and HOCl. So HOCl is called as hypochlorous acid. It's called a hypochlorous acid, highly unstable. So this will come out as OH minus and Cl plus. We told you it is a electrophilic addition. So what happens is when we react with, let us say, ethylene CH2, I would put it this way. We have CH2 double bond CH2 plus you have HOCl, which splits to form OH minus and Cl plus. So Cl plus is called as chloronium ion. So chloronium ion is the attacking reagent. So what is it going to form? It's going to form CH2. This becomes the carbonium ion because the electron shift took place, electromeric effect. So you have HCl, and then of course you have the OH minus attacking it. So you end up with what? CH2 OH CH2Cl. So this kind of compound, when at alpha beta position there is what you call hydroxyl group and a chlorine group, we call this as chlorohydrin. So this is ethylene chlorohydrin. So this is ethylene chlorohydrin. Next reaction, that is ozonolysis. Ozonolysis, this reaction can also be called as formation of aldehyde or ketone. Formation of aldehyde or ketone. So when you talk of formation of aldehyde or ketone, see what happens is, I take the simplest alkene, CH2 double bond CH2, that is ethene. When I react with ozone O3, what happens? Both the bonds are, ozone is a highly reactive substance. So it breaks both the bonds, the sigma as well as the pi. And what do I get? CH2. So this is how the pi bond broke. And here you have in the sigma bond. So this compound intermediate will be called as ozonide. So you have a ethylene ozonide. So this will be ethylene ozonide. Now moment you react this with zinc in presence of water, okay, so or water in presence of zinc, let me be more clear. So when you react with water, what happens is the bond breaks like this. So here this bond will come over here, okay, and this bond will come over here, and this oxygen will get attached to this water. So you'll get peroxide. So what happens is, therefore you get 2 moles of HC double bond OH, that is formaldehyde, plus H2O2. Now here this is where the problem is. H2O2 is both an oxidizing as well as reducing agent, and aldehydes undergo oxidation very easily. So therefore what happens is, in order to prevent the further oxidation of the aldehyde to acid, we add zinc. So the purpose of adding zinc is, zinc immediately reacts with hydrogen peroxide to form zinc oxide and water. So this is the role of, so it decomposes the hydrogen peroxide formed. Is this point clear? So if I take, let us say, isobutylene, okay, if I take isobutylene, I will end up with a ketone. So I have CH3 double bond CH2. So this is isobutylene, and this, when I react with ozone, I get a ozonide. So the structure of the ozonide will be CH3 CO CH2 O CH3. So this, when I react with water, this oxygen will come over here. So this bond will get, and this bond will break. So this becomes a double bond and this becomes a double bond. So what will you get? You get CH3 C double bond O CH3 plus HC double bond OH plus H2O2. So I told you, this reaction has to be done in presence of zinc. Why? Because then zinc reacts further with the hydrogen peroxide, forms zinc oxide plus water. So this is an important reaction ozonolysis, because this is used for finding out. And what is the idea behind this is, one of the idea is, from the breakaway, the disintegrating product, we will know at which position the double bond is. So if a very big chain with some double bond, 6th position, 7th position, or 9th position, how will we know? We'll do ozonolysis, break it, and from the fragments we will then come to know what is the position of the carbon-carbon double bond. Is this point clear? Now, how do we test for what you call presence of alkene? The 7th reaction is what is used for test for presence of alkene, that is formation of glycol. So what is a glycol? It's a 1,2-diol. It's generally 1,2-diol. So the OH group is in adjacent position. So what is the reagent for that? The reagent we use is alkaline KMnO4. Alkaline KMnO4 is also called as Bayer's reagent. It's a very simple test. You know what we do? We just take the substance, add 2 drops of alkaline KMnO4. If it is not an alkene, it will leave a violet color. If it is an alkene, the bonds will break, hydroxylation will, the reaction will take place, and then what is going to happen is it will decolorize. So the decolorization of alkaline KMnO4 is a sure shot test for what? For presence of double bond. Okay, so this is a test for unsaturation. So this is also called as hydroxylation. So you have, suppose, ethylene CH2 double bond CH2 plus, what do we have? Plus we have H2, okay, plus a nascent oxygen. What is the source of nascent oxygen? Source of nascent oxygen is alkaline KMnO4. Very important, right? It's alkaline KMnO4. So you end up with CH2OH, CH2OH. So this compound is called as ethylene glycol. So you have 2 drops, it provides the oxygen, reaction takes place, KMnO4 gets converted into MnO2. Is this clear? It releases oxygen that combines with water, and then they react with ethylene, and then they form ethylene glycol. Is this clear? And this test is called as Bayer. So remember, it's 1 or 2 drops only that we have to add. You can't add as equal to that much of the reagent, because then the violet color will still be retained, because all the alkenes have got hydroxylated and few little bit of excess KMnO4 is still there. So that's why I'm very clear specifying it's 1 or 2 drops of alkaline KMnO4. Now this is a very interesting reaction of alkene is directly you can add an aldehyde group. A quick short method of preparation of aldehyde, because aldehydes are terminal compounds. Na? Aldehydes are terminal terminal functional groups. Is it clear? See what happens, suppose if you take ethylene, CH2 double bond CH2, this reaction is also called as oxo reaction or hydroformylation. Reacted with carbon monoxide and hydrogen in presence of cobalt as catalyst at around 150 degrees centigrade under high pressure. So when you fulfill all these conditions, simply ethylene will become propionaldehyde. You have CH3, CH2, C double bond OH. So what happens is a direct terminal aldehyde group is introduced. So ethylene, also this is going up the group. Na? You had ethylene with 2 carbon atoms, you have propionaldehyde, or I can say propanol with 3 carbon atoms. But if you take an unsymmetrical alkene, suppose if I take CH3, CH double bond CH2, that is propene, and react with carbon monoxide. So this would be more relevant from the entrance exam point of view. So you react with carbon monoxide and hydrogen in presence of cobalt as catalyst, 150 degrees centigrade pressure. You get CH3, CH2, CH2, C double bond OH, and this is one butanol. And what do you get? And you will get a mixture of isobutyraldehyde, that is CH3, CH, CH3, C double bond OH. So this will be 2-methyl propanol. So this will be 2-methyl propanol. So this is a very important reaction. If you see JE paper, many a times they have asked this oxo reaction, that is hydroformylation. Formylation means introduction of a formyl group. CHC double bond OH is formaldehyde. So if you remove H, that will be a formyl group, formyl acetyl. So that way. Is this point clear? Now we saw how we can directly form what you call aldehyde straight away. So similarly, when we come to Cox reaction, same only thing is when you take an alkene CH2 double bond CH2, you take carbon monoxide instead of hydrogen. If you take water, okay, what happens is you will end up with I just will find out what is the catalyst we can use. Yeah, they have just said mineral acid. So what will happen is you will get CH3, CH2, COOH. So this becomes propionic acid. So when you take an unsymmetrical alkene, you have CH3, CH double bond CH2 plus carbon monoxide plus H2O in presence of a mineral acid. What happens is you get a isomeric. So you will get COOH. So this will be 2-methyl propanoic acid. So slight change in the reaction. If you use hydrogen and cobalt as catalyst with carbon monoxide, that will be a hydroformylation and you will get aldehyde directly an aldehyde group, and in Cox reaction will take directly a carboxyl group. It's a very interesting reaction. We come to the 10th reaction, that is oxidation. How can we conduct oxidation? By acidified KMNO4. So you must pay attention over here because the products are slightly different as far as terminal alkene and non-terminal alkene is concerned. So when you have a terminal alkene, suppose we have CH3, CH3 double bond CH2. This is isobutylene. When you react with acidified KMNO4, the bond breaks. You end up over here CH3 C double bond OCH3, that is acetone plus CO2 plus H2. So in case of terminal alkene, carbon dioxide will be evolved. But in case of non-terminal alkene, you have CH3 double bond CH3, which is 2-butene. When you reoxidize this with acidified KMNO4, what happens is you get CH3, 2 moles of straight away CH3C double bond OH. You get acetic acid. So this is the difference. So when they say oxidation with acidified acidified potassium permanganate, read the question carefully. Are they talking about terminal or non-terminal? Or they may ask which alkene will give carbon dioxide, or which alkene will turn lime water milky when you treat with acidified KMNO4. So the gases evolved when treated with lime water will turn milky. That means they're trying to stop the same thing which will release carbon, what do you call, dioxide. Is this clear? Now I am coming to see, I told you the characteristic reaction shown by Alkene is electrophilic addition. Is this clear? But it does show rare what you call substitution reaction, which we call as allylic substitution. What happens is that when you suppose you take propene, CH3, CH double bond CH2. If you remember, I told you this is one propenyl, this is two propenyl, and this is allyl. So when you have at least one allyl hydrogen, you react either with chlorine or bromine at a very high temperature of 500 to 600 degrees centigrade. Instead of addition across the double bond, what happens is there is addition on the allylic carbon. Are you understanding? So you will have 3-chloropropene. So this is called as allylic substitution, because what's going to happen, substitute will form HCl. Why is not an addition reaction? Because two reactions form two products. Addition means two reactant forms one product. So it's a substitution. So instead of the H over here at the allylic position, at least one, even if one allylic hydrogen is there, the reaction will take place. Is this point clear? So for example, let us take this. We have CH3, CH2, CH double bond CH2. So what is this? This is 1-butene. So this will be the allylic hydrogen. So what is going to happen? This is the kind of question which is asked. They don't ask propene. They would rather ask 1-butene. So when they ask 1-butene, so this is the double bond. So functional group carbon atom after that is alpha carbon atom, hydrogen on that is alpha. So that is the allylic. So you will get CH3, CH. So this is the allylic hydrogen substituted, and you have CH double bond CH2. So this will be 1, 2, 3. So this is 3-chloro, whatever, but-1-ene. But-1-ene. So understand this. Here, even here, this is the allylic hydrogen, not here. This is what will get substituted. Is this point clear? Have you understood? Now what happens is when we talk of isomerization, if you take say 1-butene, CH3, CH2, CH double bond CH2 and treat it at a very high temperature. So you have 1-butene, very high temperature alone at 500 degrees, 500 to 700 degrees centigrade. The position changes. You get CH3, CH double bond CH, CH3. So 1-butene becomes 2-butene. So this will be a positional isomerism. But when you treat with, let us say, aluminium sulfate, with aluminium sulfate Al2SO4 whole thrice, the same reaction can happen, or sometimes, see, one is again this can form, other conditions differ. The other possibility is branching can happen. So suppose if I have CH3CH double bond CH3, so this is 2-butene. So what can happen over here is, in presence of aluminium sulfate Al2SO4 whole thrice, you will get CH3C, CH3 double bond CH2. So 2-butene will become isobutylene. So look at the answer carefully. Either they could form positional isomer, or that is aluminium sulfate. Either they form positional isomer like this, or they can cause forming of a branched isomer. So this is positional isomer and this is formation of a structural isomer. Is this clear? So this is about what do you call, there is one more reaction, there is polymerization, which we will be studying in great detail in a chapter called as polymers in 12th standard. So I am skipping that over here. Okay.